So we first came across transformations when we were looking at quadratics. There are three kinds of transformations. Who can give me one of them? Is that you, Alex? Yes. Dilation is one of them. Viresh, translation is another one. Jack. Yes, Eva, reflection. So these are the three transformations that we can create on a function. Now, I want to remind you, I hope that this will fit in here okay. Each transformation transforms x, the x coordinate, or the y coordinate. Do you remember? So a dilation will cause the x or y coordinate to be scaled up or scaled down. So it'll be 3 times its position or a third of its position. A reflection changes it from being positive to negative or from negative to positive. A translation moves the coordinate either up, down, left, or right by a certain number of units. I'm hoping this is just reminder stuff for you. So each transformation transforms x or y. And the thing I wanted to point out with the y transformation, when we transform y transformations affect the whole rule. Okay? So we have an x coordinate, and now the x variable is like the independent variable for those of you who are science-minded. It travels along from 0 to 1 to 2 to 3 to 3.1 to pi to it has its own value. There's a rule which gives us a corresponding y value. So the value of y depends on what the value of x is by applying a rule. So if the rule was 2x, that means the y coordinate is given by whatever the x coordinate is and then doubling it. So when we transform the y coordinate, we're actually transforming the rule 2x in that example. What do you think so far? Does that make sense? Okay. You were worried I was going to pick on you then, weren't you, Harriet? No, I was just looking around the room. Okay, so that's the key thing here. Generally speaking then, what the name of the game is that it takes a base or parent graph and turns it into a new graph. And we have seen that with quadratics. The actual picture of the graph itself can get thinner or longer, or it can flip upside down, or it can move from the origin to somewhere else on the axis, but that's the effect of the transformations. Right now, I'm just talking effects. We'll have a look at specifics in a sec, or remind you of the specifics. So for cubics, the base graph is y equals x cubed. And if you remember, that looks like that. It doesn't have a turning point. It has an, Alex, star pupil today, inflection. Okay, it has an inflection. Okay, they are both called stationary points because effectively the graph is still at that point and then moves off again. So turning points and inflections are both stationary points, but it is called an inflection. The transformed graph is either like that or like that. Now, why am I going to graph? It seems pretty obvious to me that if that's the original graph, the new graph is going to look the same except stretched or squished or whatever else. But also it might look like that in that it's reflected. Why have I pointed that out rather than just that being an obvious fact? This is me going on a fishing expedition. I've got something that I want from your brains, but I'm probably not being clear with what I'm looking for. But I'll give it a moment in case someone connects with what I'm saying. But it's me, not you, if you can't get it. Max? You can flip X and you can flip Y. You can do both of those things, so that's fine. No, this fishing expedition is not... Oh, yeah, go. It's not. The fact that I've said it could be either of these shapes is not what I'm going for. It's okay. It's me being unclear. My point is that there is another shape, right? There's this shape here for a cubic, yeah? So my point is that when you transform the base cubic, you'll get something with an inflection in it. You won't get something with two turning points like this, okay? So it will only transform to this. Of course, you can transform any function. You can transform a cubic that looks like that into a different function that maybe looks like that, but it's just that neither of these are considered the base function y equals x cubed. That's my point there. Okay, any graph, remember, any function can be transformed. So it won't convert or transform to this. I don't mean to put arrows on it, confusing, or this. Okay, it doesn't convert to a roller coaster. Okay, good so far? All right, language time. Administrations, information sheets. Okay, this is just to remind you that your information sheet lists the transformations here. You have your information sheet for tests, for exams. This is your friend. Because this is just a reminder, I'm just going to talk to it, but you can stop me if you're not too sure. So this talks about reflections first of all. So y equals negative f of x. We're taking the function and we're making it negative. So this reflects the graph. I say about, but they say in the x-axis. So this causes it to flip. I have to do this in the air, so it's not great for the video. It causes it to flip that way, okay, around the x-axis. Y equals f of negative x. What you can see here is that the function now has its inputs transformed, okay? So the reflection happens around or in the y-axis. So again, physically, I'm talking about it flipping that way, okay? It's flipping that way. That's the result of transforming by making the input negative. So what was negative is positive, what was positive is negative, so it flips that way. Y equals a multiplied by f of x. So what we're doing is we are taking the function and we are multiplying the old coordinate, which is f of x, by a. So that is called a dilation of the graph by a factor of a in the direction of the y-axis, which means that it's stretching that way or compressing that way. But the direction of that stretch is parallel to the y-axis, or the direction of the compression is parallel to the y-axis. So that's why it says in the direction of the y-axis. The dilation stretches it away or compresses it towards the x-axis, but the actual shape of it is going parallel to the y-axis. Okay with that so far? This is just hopefully reminder work. y equals f of ax. So we're replacing x with ax. So we are causing the function to go through its values more quickly, which has the effect of squishing up the graph if a is a whole number. So when we get to transformations of the x, it always feels like counterintuitive. Remember that. So f of ax is a dilation of the graph by a factor of 1 over a. So in other words, if I have a multiplied by x, the dilation will squish the graph towards the y-axis. So let's just say I had 2x here, then the graph would be halved. Okay, maybe it might be good. I'm not confident that going through too many examples actually helps too much. But if we've got y equals x cubed here, if I go y equals 2x cubed, it's hard to see this though. Just keep that in mind. It's hard to see. 2x cubed. Question? Am I boring you? Do I need to go faster? If there are no questions and I'm not boring you, then you're just chatting. This green one here, it's hard to see, but it's effectively squished towards the y-axis because doubling what I'm cubing effectively makes it go through its values faster. So everything is squished in. Okay, it speeds through the graph faster. That's why this green line is squished in here. And that's why you could say that the distance from here to here is half the distance from here to here. Okay, so the distances from the origin have been halved all the way along here. From here to here and from here to here is halved. And that's why we say it's a factor of 1 on a. Okay, so 2x, 1 on 2. 3x, 1 on 3. If a was equal to a half, then the dilation would be stretched out because 1 on a half is equal to 2. So if I make this 0.5, you can see it's now stretched out. So the distance from here to here has been doubled to go to here in the green graph here. That's probably the hardest one to look at, really, the dilations of the x-axis. Okay, so that's what that means. And then these are kind of relatively straightforward. If I add h to the inputs, x plus h, that's a translation, h units to the left. Same counter logic. I know it says plus h, but we actually go to the left. And if we've got plus k here, so we've got the function and we're adding k to it, we're taking the old input, the old y coordinate, we're adding k to it, so it goes upwards by k units. And if k was negative, then it would go downwards by k units. So that's just a reminder about the language and the different effects that they have. But I'm going to show you some examples to make it solid from this point on. Questions before I move on, though? Is that a question? Yes. Good. So if it says x minus h, it goes to the right. If it goes x plus h, it goes to the left. Yeah, thanks, Charlie. Good one. Okay. Back to the business at hand. I'm going to try and just do as little as possible before getting you to do some practice work. So, because I'm thinking that maybe the practice will help you pretty much figure out how these transformations work, where me just talking and talking and talking won't. So here's an example of how I can apply transformations and get a new function. So let's just say the base function, let's just leave it as f of x equals x cubed. And I want to create a new function. And I'm going to do it by applying these two transformations. Number one, I'm going to translate by 2 units up. And number two, I'm going to dilate by factor of 3 in direction of y-axis. So I'm keeping it fairly simple here. Okay, so I'm going to do those two transformations on my cubic, and we're going to get a new function as a result. So first of all, I thought what might be useful is to look at the y coordinate of on that graph and see how that's transformed first of all. So I'm going to use an example of at x equals 2. At x equals 2, what does y equal? Sorry? Yeah, we're in real trouble. This should be automatic at this stage. If x equals 2, y equals 8, because the function is x cubed. Now, that tells me... Now, when I say that, I'm not saying that you don't know that 2 cubed is 8. It means that the way I've asked you it hasn't resonated with you. And that's what we're in trouble for. You're not in trouble. We're in trouble if you don't understand what I'm asking for. So sorry about that. I'm not too sure. Maybe you thought you had to do the translations in your head or something like that and then come up with a new value. But yeah, all I meant was for the base function f of x equals x cubed, if x equals 2, what would the y coordinate be? Well, it would be 2 cubed, which is 8. That's just applying the rule. Am I making sense now? Okay. I hope it's not that you didn't know that 2 cubed is 8. If it is, you can talk to me later. So that means our coordinate of our base graph is going to be start with 8. And now I'm going to apply the transformations. So transformation number 1 is translate by 2 units up. So 8 would become 10. Then I'm dilating by a factor of 3, which means that for all my y coordinates, I'm going to scale them up by a factor of 3. So what was 10 is now 30. Yeah, you did say 30. Yeah, that's all. Is that okay? In terms of our function, we apply the same ideas, except we just do it to the algebra expression rather than the number. So our base graph is x cubed. If I translate 2 units up, I'm going to get x cubed plus 2. Yeah? That's my new function, my new rule to work out every point, not just the coordinate 8 or the coordinate 2, sorry. Every single coordinate is now worked out by cubing the x coordinate and adding 2 to it. And then step 2 is to multiply by 3. So I take the old coordinate from the step before, which is x cubed plus 2, and I have to multiply it by 3. Now, I need to keep x cubed plus 2 together, so I have to put brackets around it, and then I put a 3 outside. So I get 3 outside of x cubed plus 2, which, P.S., I can simplify if I want to x cubed plus 6. It works when x equals 2, 2 cubed is 8, 8 times 3 is 24, 24 plus 6 is 30. Okay, so this is the new rule, and it doesn't, of course, just work for x equal to 2. Because I've done it with algebra instead of a number, this works for x equals 1, x equals 17, x equals pi, whatever. It works for any input I will get. This rule will give me the transformed output. Does that make sense? Okay, the next thing I want to point out is this, and that is that order matters. So, number 1. So, from the base graph of f of x equals x cubed, I am going to, number 1, dilate by a factor of 3 in direction of y-axis. I hate dilations, they're the hardest to write out. Number 2, I'm going to translate 2 units up. So we agree it's the same 2 steps but reversed. Let's have a look at the coordinate. 8 It says dilate by a factor of 3. So what would that give me? Dilate by a factor of 3 means I'm scaling up my y coordinate from 8 to 24. Great. And then I'm translating by 2 units. So 24 gets translated 2 units up to 26. So you can see it's a different coordinate, right? And it's a different rule. Let me do the rule and then you'll see it for yourself. X cubed would become 3x cubed. And then 3x cubed would become 3x cubed plus 2. So we end up with a different rule. In fact, they're very similar. They're just 4 units apart, but nevertheless, they are definitely different rules. Okay? Just real quickly, if I have a look at Desmos, this is an example of a transformation with a transform base function with a whole bunch of transformations done all at once. You can see that it is the same basic shape of a cubic with an inflection, but it's being moved down, across, it's been made thinner, etc. Okay, so all of these transformations do that. Now, since order matters, it also matters which order you write them down. Eva, you okay? You seem to be distracted. So this is the last thing I want to show you, and then you're going to do some practice around it. This is the one I just showed you. The function y equals -2 outside of 3x plus 1 all cubed minus 1 has been transformed from y equals x cubed. List the transformations, easy. In order, that's the challenge. You need to get the order right as well. Based upon the last example I showed you, you could see that putting them in the wrong order gives you a different function. So what we're trying to do is we're trying to list them in a way so that if I applied the functions in that order, I would go from x cubed to -2 outside of 3x plus 1 all cubed minus 1. It will do that. Okay, so here are the steps. I'll do the steps in red because you wouldn't write this down when you're doing this solution. But the first thing you do is if you have to, factor out the coefficient. You'll see this in practice in a second, so it'll make sense. If there is one, factor out the coefficient of x. So in this case, and I'll do the example properly in a second, the coefficient of x is 3. There's a 3 in front of the x. So you need to factor that out first. Okay? You need to factor that out first. Number 2, list the transformations in alphabetical order. More than one order works, but this one is just nice and simple to remember. Alphabetical order, DRT. Okay? So you look at the equation and you say, what dilations has occurred? What reflections have occurred? What translations have occurred? So you can have up to 6. Okay? And you just go, it doesn't matter which order you do it, but I tend to go input output. So X and then Y, then X and Y, then X and Y, but it doesn't really matter. But you can only do that if you've done step 1. If you forget step 1, then the transformations will be wrong if you just go DRT. So step 1 is critical. So let's see this in action. So first of all, we take the function and we factor out the coefficient of 3. So it's minus 2 outside of 3 outside of x plus 1/3 all cubed minus 1. So the only thing I've changed is the inside here. Now, I'll just show you that it does work. If I go backwards, 3 times x is 3x. 3 times 1/3 is 1. So factoring out that 3 gives me a new looking function, but it is in fact an identical rule. If I put any value of x I put in here will give me a value for y, which is exactly the same as this. So these rules are equivalent. Okay, so I do that first. It's a bit of a pain in the bum to do. It feels like, oh man, do I have to do that because now I'm dealing with fractions? But it makes the rest of it, trust me, it makes the rest of it easier. Now the transformations are one, DRT. So can we see a dilation of the x? We can. It's right there. It's inside the cube. And so we can see there's a dilation of 3 here, or sorry, the number 3 is here. And so we can say, again, it's just tedious to write out, dilation by factor, not 3, but 1/3. Remember, 1 on A. Dilation by factor 1/3 in direction of x-axis. Are there any more dilations? Has the thing that has been cubed been multiplied by something? Yeah, what is it, Esther? Good answer, but not 100% correct. It has been multiplied by -2, so that's good. But -2 is not the dilation, though. What's the dilation? Do you know, Tash? It's not 1/2. I see where you're going there. It's the fact that it's a negative is the problem. Jack, it's just 2. So when you see -2, like you did, -2 is in fact 2 transformations. It's a reflection and a dilation. So we just write the dilation down. So that was a trap for young players, that one. Dilation by factor 2 in direction of y-axis. Yes, so it's the ones inside the cube, the things that are hitting, are affecting the x effectively. They're the ones that get sort of reversed. Yep. It's one of those things that I think I can explain the logic behind it 50 times, but ultimately at some point it'll probably click, but it's probably just a matter of that I'll just memorize it, just remember that kind of thing until it's right, do enough problems until it's right. So that's D done, DRT, dirt. So done dirt, got ERT to go. So is there a reflection about the x-axis? Is there a reflection that affects the x? In other words, is there a negative next to the x? No. So there's no reflection about the y-axis. Is there a negative that affects the whole function, cube? Yes, there is. So there is a reflection. So there's a reflection in the y-axis. Okay, that's R done. D, R, and then the fourth one is the the next two are translations. Is there a translation that is inside the cube? Yep. What is it? Sorry? It is. It's a third. Which direction? Think counterintuitive, left or right? Left. Well done. So, translation. Left by 1/3 units. And number 5, there's a translation. One unit down. Good. down by 1 unit. And that's our 5 transformations in order. It feels weird to talk about a transformation of a third when there's no third in the original function that you're given, but it does work. And I'm just conscious of time and giving you practice time. So I might come back another time just to unpack this again for you. But it does work. If I went x cubed and then did these 5 translations to x cubed, I would be able to get this function here. But I won't do it today just so that you've got time to practice. Charlie. So don't think BODMAS or anything like that. Just think of it really simply, is that the transformations have to be listed in alphabetical order. Now, I could have swapped these two around, and that's no drama at all. I could swap these two around, and it's no drama at all. So there's no magic. There's no magic thing of whether you need to put X before Y or Y before X. You just need to make sure that you're listing the dilations first, the reflections second, and the translations third. Yep. Okay, so like I said, I'll come back into it. What I'm going to get you to do, I just need to run down and grab it from the photocopier. But what I'm going to get you to do is this little worksheet I've done up, because the textbook's no good for it really. And in the first question, there is a single transformation that has been applied to each of these problems, and you just need to write it down. You can't go wrong, because when you've only got one transformation, it's really hard to get it out of order, right? And in the second one, there's a whole bunch which require multiple transformations. I've given you 4 lines. Not all of them require 4 lines. Okay, so I'm just going to go grab that, and that will be your work for the rest of the afternoon.